I wanted to tell you about new stuff which builds on what I've been doing and also lays a path forward for really what I want to do in the next few years. And in general, this is about galaxy formation, and in particular, this is about the multi-phase flows into and out of galaxies. So to give a little background, I think most of you, when I say a galaxy, imagine something like this. Here's my little, iPad cartoon here of a galaxy. But this is not enough to think of when you think of a galaxy and galaxy formation. You really need to think of the galaxy in its entire surrounding circumgalactic medium, which is the diffuse massive reservoir of gas that surrounds all galaxies. And the reason why you need to think about this is because this is where inflows and outflows combine together and interact and set the fuel supply available for star formation and black hole growth, and really which shape galaxies. And so if you want to think about galaxy formation, well, this is galaxy formation, not just the little purple squiggle in the middle. Okay, so today we're going to talk about one specific aspect of this, which is the outflow side of things. So here is the iconic example of a galactic wind, of an outflow. This is M82. Here you can see in greenish the stars, and here in blue and red you can see this incredibly powerful outflow flying out of this galaxy. And this is an iconic example because it's close and it's very powerful, but galactic winds are crucial for galaxy evolution throughout cosmic time. And so we really need to understand this process if we hope to understand galaxy formation. And really, not everyone in the audience cares about galaxies for themselves. So if you want to understand star formation and black hole growth, you need to understand this. If you want to understand cosmology and use galaxies as a tracer for the structure of the universe, you need to understand this. So although this may seem a little specific, it's actually a very broad question. And the techniques we're going to use to get at this actually span a very wide range of fields and subfields, as you'll see. So we'll start by talking about what actually drives the winds. So from within the galaxy, how are these winds powered? Then we'll move out into the winds themselves and look at the properties of the winds. And in particular, in this M82 example, there is 10,000 degree gas shown in red, moving at thousands of kilometers per second. And so there's also some 10 million Kelvin gas moving incredibly fast. And so there is a rich structure and properties of these winds that we need to understand if we hope to understand this system. And we'll end by talking about the impact of these winds on galaxy formation in general and their sort of large scale structure. Okay, so I'm just seeing everyone's congratulations in the chat. Thank you very much. Okay, cool. So let's begin. Let's get into the galaxy itself. All right. And to start, I'll show you a very cool simulation run by Chang-gu Kim, which shows a small patch of a galaxy. So imagine you have this big galaxy and you take just a little patch of it, okay? And what we're seeing is this galaxy edge on. So here is the mid-plane of the galaxy, and the simulation domain extends above and below. And you'll see the density, metallicity, temperature, velocity, and magnetic field strength in these simulations. And this analysis that I'm going to show you is from a recent paper we put out just a few months ago as part of the SMOG collaboration. And let's focus here on the middle panel. And what you'll see is stars form, live, and then die and explode. And when they do, these powerful explosions, these supernova remnants, blast through the interstellar medium, sweep up cold gas, and launch out these really vibrant and rich outflows, which have an incredibly complex structure with cold gas and hot gas moving at a range of velocities. And so this gives us a good window into how winds are actually driven. And we can look at this a little more quantitatively by looking at the phase distribution of these outflows. So what this plot on the right shows is the fraction of the mass flux at a given sound speed, so the temperature, versus the outflow velocity. And what you can see here is a very generic trend, but it's also a very puzzling trend. Most of the mass flying out of these galaxies is cold, or I'll call it cool gas, at about 10,000 Kelvin, okay, a sound speed of about 10 kilometers per second. And it's only flying out of the galaxy at about 30 kilometers per second. So the escape velocities of these galaxies are far, far higher than 30 kilometers per second. So this mass flux is not going to really make it far out of the galaxy at all. Most of the energy, though, is carried by this very, very hot, very fast moving phase that's going upwards of 1,000 kilometers per second, just like we saw in M82. So this is great. It tells us a lot, but it also poses a conundrum, which is, you know, in M82 and in almost all models of galaxy formation, you have a sizable mass flux out of the galaxy. So how do you take this cool gas here and accelerate it up to these higher velocities? That's what we'll talk about today. So I'll say this is not unique to these very high resolution, very realistic patch simulations. Viraj Pandya, a pre-doctoral fellow here, and I are about to put out a paper looking at the exact same thing in the Fire 2 cosmological simulations. And I'm not going to get into too many details on this other than to stress that the same thing, here's that same phase structure. Now it's temperature instead of sound speed. But again, most of the energy is carried by this very fast moving hot phase, but most of the mass is down here, and we actually shaded it out because it's not moving fast enough to escape the galaxy. So we're going to zoom into this process and see if we can't understand better the process of accelerating one of these cold clouds, okay? So here is one of my simulations from a few years ago, and we've now zoomed in onto just a single superbubble in the interstellar medium. So this is one of those patches of the interstellar medium. I've now rotated it on the side. So you're seeing the disk midplane is oriented vertically. And this blue, this is going to be a visualization of the temperature. And the bluish white color is cold, sort of molecular gas at around 10 to 100 Kelvin. The bluish black material is the warm ionized medium, which is around 10,000 Kelvin. And pretty soon you'll see I'm going to start setting off supernovae in the middle of this domain, which is going to heat up gas up to tens of millions of Kelvin, which will be in bright yellow. So here we go. The supernovae start to go off. They inflate this bubble in the middle of the interstellar medium, which begins to break out. And it breaks out of one side and then the other. And as it evolves, you can see there's this hot vent that's blown, and it's allowing gas to flow out of the galaxy. And all the while, cold gas is being added to this sort of hot wind tunnel that's been blown through the galaxy. And as the cold gas is added, it's shredded and accelerated. And so you can see these clouds have just been added here. And in some cases, they're sort of fully shredded and obliterated. And in other cases, you have cold clouds that can sort of make it all the way to the edge of the box. And so I'll pick a single freeze frame here, and we can understand this in a little more detail. So the supernovae are going off here. They're blowing this very, very hot wind out of the galaxy. And you can see here, I've highlighted two clouds. One is just starting to get hit by the wind, and the other has already been pushed and accelerated up out of the disk and is starting to, reach these high velocities and flow out of the simulation domain. And it's importantly developed this long tail. Okay, So we've already zoomed in from the whole galaxy onto a patch of the galaxy and now onto an individual supernova remnant. And I want to zoom in one more time onto an individual cloud. Okay, and let's just try to really understand this in a very controlled environment where we're going to take a single cloud and hit it with a hot wind. This is a problem that's been studied in great detail for 30 years, 25 years. But we've just had some major new insights that have changed the way we think about this. And these visualizations are coming from a paper that we put out just last week with Matthew Abruzzo, a Columbia graduate student. And what, in this case, the blue color is going to be the hot dilute wind, and it's going to move past this cold, dense cloud. And we're going to ask, what can I push on this cloud and get it to accelerate? And you can see when I start to push on it, I get this turbulent wake. And the turbulent wake shreds the cloud apart. And we have this problem, and I should mention the frame of this visualization is tracking the cloud. And there's a problem in these simulations, I'll play it again, which is that the clouds are mixed into the background medium on a much faster time scale than they're accelerated. Okay, and so we can understand this quite simply. You know, we've all studied sort of the turbulent wake behind a baseball in a high Reynolds number flow, right? That turbulent wake acts as a drag force and it accelerates the cloud. But the drag in this case, you know, for a baseball is a solid object, so the turbulence doesn't do anything to the ball itself. But for this gas cloud, the turbulence actually shreds and destroys the cloud. So that is the problem in a nutshell. And when we look at this quantitatively, it turns out that the mixing time for these clouds is shorter than the drag time by a factor of about chi to the 1/2 power. You can see this has a chi to the 1/2, this has just a chi. And chi here is the density contrast, so the ratio of the cloud density to the wind density. And for these galactic wind systems that we're interested in, this is often a value of 1,000, but sometimes it's even higher than that, of about 10,000 or so. Okay, fine. So this cloud, it's going to be shredded and it's going to lose mass at a rate given by roughly the cloud mass divided by the mixing time. Sigurd, yeah, maybe we haven't all studied the turbulent wake. I don't know. Okay, so good. So if this were the end of the story, this would be a pretty depressing talk, because what this says is that we don't know how to accelerate these clouds, but that's not the case. And the reason why is cooling. Cooling comes to the rescue. So here is an otherwise identical simulation where we've now included radiative cooling. And you're going to see what's happened. The turbulent wake starts to form, but now the hot phase actually condenses down onto the turbulent wake, and the cloud actually grows in time. Okay, and so this is a fundamentally new picture and solves the problem of not being able to push on the cloud, because now when we push on it, it not only stays together, it actually grows. And for those of you who don't think about this all the time, I'll explain this in a little more detail. Here, what I'm showing is the cooling time as a function of temperature. Okay, so the cold stuff, which I said is at about 10 to the 4 Kelvin, has a very, very long cooling time, upwards of a gigayear, as does the hot stuff. But once you mix the two, right, what does this turbulent wake do? It mixes the hot stuff and the cold stuff, just like, you know, milk and coffee when you stir it. So by mixing the two, you populate this intermediate temperature regime, which cools like crazy. It cools almost 4 orders of magnitude more rapidly at a fraction of a megayear. And so when that cooling time is faster than the mixing time, the cloud can grow. But how fast does the cloud grow? This is the key question that remains to us. We're going to answer this question, and then that's it for the details, and I'm going to build it all back up because we've been zooming in, and I'm pleased to say we're going to zoom in one more time. So here is my cloud wind interaction, a little cartoon. I recently had a great meeting with the Flatiron's graphic designer, and she's going to help me improve my cartoon game. Although she liked this one, so we'll see what she does. So we're going to take this cloud wind interaction. We're going to zoom in on the skin one more time, and we're going to study the turbulent radiative mixing layer that separates the cold cloud from the hot wind. And these TRML, or turmoil, as we like to call it. Excuse sort of the lame puns, but it's useful to have a word for them. So these TRML, or the turmoils, are what we'll talk about next. And so when we look at this shear flow, what we have is, let me adjust the size a little bit. Cool. So we have a shear flow between the hot and the cold phase. And that is, of course, unstable to the Kelvin-Helmholtz instability, which gives way to turbulence. And that turbulence leads to mixing. And that mixing, as I said, populates the intermediate temperature regime, which can cool like crazy. And once you have that cooling, well, that cooling is removing energy from the interface layer. And in an effort to maintain energy balance, what's going to happen is there will be a net flow of material, condensation from the hot phase down onto the cool phase, which explains why the cold clouds actually grow. And so we can see this in practice here, looking at one of my simulations from a paper we put out last year. This is going to be a visualization on the left of temperature, or hot is on top, cold is on the bottom. The middle is the turbulent velocity, and the right-hand side is the inflow velocity, where blue means a flow from the hot phase into the cold phase. And so the initial shear flow gives way to Kelvin-Helmholtz, which gives way to turbulence, and that turbulence leads to mixing, which populates the intermediate temperature regime, as we said, and that then cools like crazy, which leads to a net inflow, as you can see here in this blue color. Okay, so these are some controlled, idealized simulations I ran. These are actually not from the paper. These are from a recent project I've been doing with Shirley Ho, Miles Cranmer, and some other people, including a team from Google's DeepMind, to use machine learning to actually accelerate and better understand these simulations. Although I will say, I think we've got a pretty good understanding. And in this paper that I wrote with Eve Ostreicher, Greg Bryan, and Adam Germain, what we did is we realized that this interface between the hot and the cold is very bumpy and wiggly. And you can be a little more quantitative than just bumpy and wiggly, and you can measure its fractal dimension. And it turns out that this surface has a fractal dimension equal to this little line I've drawn over the top. And you can see they're actually quite similar. And by appreciating the fractal nature of this interface, we were able to uniquely write down an expression for how this cold phase grows. Okay, and this expression may seem a little obscure, but it's really not so complicated. You have the density times the area times the turbulent velocity times this factor here, which is, R cloud divided by V turb. That's just the mixing time, right? That's the eddy turnover time. And that's divided by the cooling time. And this is all going to be risen to some power alpha, which can be one of two things, okay? It can either be a quarter or a half. And without getting into too much of a really quantitative description about this, the distinction between a quarter and a half happens when you're in the rapid cooling limit or the slow cooling limit. And I'll give you an analogy for how you can understand this. Imagine you've got a locomotive, okay? You've got a steam engine, and you ask how much, how fast can my steam engine go? Well, if the furnace is already roaring hot, then the rate limiting step is how fast the stoker can shovel more coal into the furnace. Okay, and so in this analogy, that's how fast can turbulence mix in new hot gas. That's this upper limit. And on the other hand, imagine you're just starting up the furnace. So you put a pile of coal in the furnace and you light one side and you ask, the heat will slowly diffuse through your pile of coal. So that's a hand wavy description of why you have these two limits. But the important thing for us today is that we have this relatively straightforward expression for the mass growth. Okay, so I'm glad you guys have all bared with me. We've gone down and down and down and down and down. We've zoomed in 5 times, and now we're gonna put it all together, okay? And this is where things really get exciting, and this is where my graphic design skills are really gonna be on display, or really where I am in desperate need of some help from Lucy, our graphic designer. So here's a galaxy, okay? And here's the way this process works. You have some supernovae go off, as we saw. Those supernovae heat gas up to millions of Kelvin, and it starts to accelerate these gas at hundreds to thousands of kilometers per second. As those supernovae begin to move through the galaxy, they're going to sweep up many different clouds of different sizes. Okay, you'll have small clouds and big clouds, and they'll all be roughly 10,000 Kelvin. And as the wind starts to accelerate by them, it's going to try to sweep them up and accelerate them. But as we saw, different clouds are going to be accelerated differently. So we can zoom in on an individual cloud like we've just done. And as we've learned, there's a competition at play, right? The clouds are trying to grow due to this condensation, but the turbulent wake is also trying to shred them apart. And we now know exactly how these two expressions work, right? So the cloud growth is given by this expression I showed on the last slide, which is it's really just the cloud mass. This B turb over our cloud, that's 1 over the mixing time, and then times this C to the alpha, where C is again the mixing time to the cooling time. So while this isn't the most intuitive expression, and that's why we only just recently discovered it, it's actually quite simple once you see it. And that is going to be pitted against the cloud loss, which again just goes as the cloud mass divided by the mixing time. So we put these two together and we get this sort of beautifully simple expression. Okay, this is the total mass growth of a cloud. And what you see here is that when C is greater than 1, which means cooling is faster than mixing, so C is positive or is greater than 1, this whole thing is positive. So the cloud will grow. And I know C is maybe not the most intuitive thing to think about. So it's simpler to just think all other things being equal, C is linearly proportional to the cloud radius. So big clouds grow and small clouds are shredded, and small clouds are defined to be when the mixing time is faster than the cooling time. Okay, so that's all encapsulated. Pretty much everything that I've talked you through so far is encapsulated in this one simple equation. So as we now know, small clouds are shredded, just like we saw in Matthew's simulations, and large clouds grow. And this all comes together into a sort of coherent picture where the initial wind, which is very hot and doesn't have very much mass, actually is mass loaded by shredding and eating the small clouds. But the cold phase survives and persists out into the surrounding medium in the form of large clouds that weren't shredded. Okay, so there's my cartoon. And in the final few minutes, I want to put this together into a coherent picture for everyone and really explain what this means. So we'll get a little quantitative. maybe not that quantitative. I don't want to put everyone to sleep by walking through all these equations, but I show these for a reason, which is to say that, you can write down everything that I just described in a very manageable, useful form. And it's really not that complicated. It's just the mass, momentum, and energy conservation equations with source terms that describe the transfer of mass, energy, and momentum between the cold clouds and the hot winds. And that's these equations here. And with these, you can solve for the structure of the wind. Phil, I see you looking closely at these. We can put these back up at the end, but I want to show you what one of these solutions look like. And of all the beautiful simulation movies I've ever made, all the plots I've ever made, all the graphics I've ever made, I truly believe this is the most beautiful plot I have ever made. It encapsulates pretty much everything I've ever studied. And what it shows here is the radial velocity in a galactic wind of the hot phase and of the cold phase. And so you can see the cold phase is initially moving slowly, and it's going to be gradually accelerated up to nearly the same speed as the hot phase. And this simple plot has all of these, rich dynamics embedded in it. And we can make it more complicated, of course. Here, I'm showing not just a single cloud species, but small clouds up to large clouds. And you can see exactly what we saw, that the small clouds are shredded and destroyed, whereas the large clouds survive and accelerate more slowly. I've also added the sound speed in addition to the outflow velocity. And in gray here, I'm comparing it to the case where you don't have any cold clouds. And you can see that the presence of cold clouds, this whole process isn't only important for the cold clouds, it actually changes the properties of the hot wind itself. And so there's a ton of things you can look at here, and I'll only show one crucial property, which is what we started with. You remember I showed Chang-Gu's simulations in our analysis of the phase structure, which was also seen in Virage's analysis of the fire simulations. And what we saw there was that most of the mass at the base of the winds was flying out in the cold phase. This is showing the mass flux in the cold phase versus the hot phase as a function of radius. And what this model is able to capture is the transfer of material from the cold phase to the hot phase without fully destroying the cold phase. You can see it here is still present, although most of the mass has been shredded away. And this might seem a little sort of obscure, but I want to show some of the utility of this, which is threefold. One is it helps us understand some simulations like this one here. This is a really incredible simulation done by a dear friend of mine, Evan Schneider. And this simulation cost 100 million CPU hours. It was a monolithic effort to simulate one idealized galaxy and try to do it at high enough resolution that you could resolve the clouds. And they did this, and they analyzed it, and they got some properties of the winds that they didn't know how to understand. And that I myself have, this was a huge motivation for diving into this. In particular, the temperature was different than they expected, the velocity was lower than they expected, and the cold phase velocity gradually accelerated, while there was a net transfer of material from the cold phase to the hot phase. All of these properties exactly fall out of my model. So that, honestly, the first time I made this plot, I sent it to Greg and Elliot and my other collaborators, and it was just like, oh my God, we got it, because this is 100 million CPU hour simulation. You can do one, maybe two of these. But now with this model, we can identify the salient physical processes controlling this structure and do it for free and do a whole range of models, knowing that we've got the right dynamics. And this is going to be hugely powerful because it's going to enable us to use this as the backbone for understanding multi-phase galactic wind observation. So here's M82 again. And Greg, Brian, and I just put in an NSF AAG proposal to hire a student to do detailed observational modeling using this. So a lot more on this to come. I'm really excited about this. And lastly, I'll just end with my baby. So many of you are in the SMOG collaboration or have heard of the SMOG collaboration. This is the crowning jewel of the SMOG collaboration. I don't know. This is a project as part of the SMOG collaboration. Sorry, that was maybe a little
Smaug's favorite toy.
So, yes, thank you, Rachel. Smaug's favorite toy, exactly. So what we're doing is using this model that I've introduced today as a totally new type of subgrid model. And this simulation I'm showing here on the right is meant to be impressively low resolution. Okay, so while Evan's simulation was impressively high resolution, this is impressively low resolution because all of the tiny, tiny small scale dynamics that would require such insanely high resolution have now been shifted to a subgrid model, unlike any subgrid model that's ever been made, that respects and captures the hydrodynamics of these interactions, allowing us to do huge volume simulations in such a way that actually has reliable hydrodynamics. And so I think as we push to larger and larger volumes, as new telescopes come online and try to understand the structure of the universe, simulations using this sort of subgrid model is going to really revolutionize things. Okay, whew, I just said a lot. So I'll wrap up and say, what I've tried to show you guys is my effort to bridge this incredibly vast range of scales relevant to galaxy formation, ranging from the megaparsec down to the subparsec, where you have the global dynamics with the interplay of inflows and outflows, which then regulate the fuel supply available in the galaxy for star formation, in the resulting winds, which depend so sensitively on the actual micro scale dynamics going on in these mixing layers, and not just drilling down, but also drilling back up and connecting this loop, because these the global scale depends on the micro scale as much as the micro scale depends on the global scale. And so not only have we used a range of scales to study this stuff, but I've tried to use a range of techniques ranging from idealized small controlled numerical experiments, cosmological simulations, a lot of analytic arguing, and even new techniques like machine learning. So that's it in a nutshell. And I'll just end by saying that although this has been a highly sort of galaxy-centric talk, I think there's a lot of really rich connections to be explored. I'm already working with Bart Raperda and Sasha Filipov, searching to explore parallels between lessons they've learned in the heliosphere, as I've shown here, and in AGN accretion disks. There's also incredibly rich connections to be explored in terrestrial atmospheres with moist convection and even volcanology. And lastly, this process of turbulent mixing layers is very, very similar to turbulent combustion. So there's lots, there's lots to do. I'm really excited to explore these things, and yeah, I'll end there. So thank you.
Thank you very much, Drummond, for that beautiful talk. So please just go ahead and raise your Zoom hand if you have a question. And I see we already have some questions. So Brian, please go ahead.
Hi, Drummond. Thank you for the excellent presentation. As someone who studied radiative shocks and the kind of cooling that happens behind those, I know one of the issues that afflicts these things sometimes are numerical conduction, and which possibly can be complicated by the magnetic field, which is anisotropic. So I guess I'm wondering, what is the role of conduction, if anything, at this interface where you're getting the mixing of the hot and cool gas? And does that affect anything, or does it just kind of once it starts mixing, you kind of don't have to worry about it anymore because it's on a much smaller scale?
Yeah, so fantastic question. The last point you just said there, I would say you've got the right insight, but I'll give a little more of an answer to that, which is one, I think my next two papers, one of which is with an undergraduate student from Columbia, and if any of you are interested in coming to the group meeting tomorrow, I will be talking about his work there. And another is a new set of these simulations of these turbulent mixing layers. And in both of these cases, we've included the effect of conduction. And there are limits in which conduction can sort of dominate the overall dynamics. But in most cases that we've been interested thus far, the sort of effective turbulent conductivity, which you get from the bulk mixing, actually far dominates over the microscale conductivity of the electrons themselves. And for the most part, you can ignore it. Although I will give one little teaser, which is that, and I guess it kind of makes sense, right? I don't want to get too into the fluid dynamics weeds here, but turbulent conductivity, well, it's not real conductivity for the first point. It's just, you're mixing these phases, but it sort of acts like a Prandtl number of 1 in that it's got a viscosity and conductivity that are comparable. Now, if you have non-unity Prandtl numbers, then the effect can actually be a little more relevant. And so this is the subject of a paper that we're aiming to have out around May or June. I've done a bunch of these simulations with explicit viscosity and conduction, and specifically varied the Prandtl number and find some interesting deviations.
Thanks.
David?
I guess you partly answered this with the comment on conduction, but I'm wondering what happens as magnetic fields become more important?
Yeah, so again, this is a great point. And this is where the beauty of having a whole bunch of different types of idealized simulations and cosmological simulations really helps us. So if you do a turbulent mixing layer and put in magnetic fields, what happens is the magnetic fields get wound up and up and up in the small scale dynamo that happens, in this, let me just go back here, in this little mixing interface. The magnetic fields will get wound up and up and up until the plasma beta reaches unity. You can start with an incredibly large plasma beta, so the magnetic field is negligible, but it will build itself to becoming very important, at which point it shuts off all mixing. However, it turns out that's actually an artifact of this periodic setup. And when you do a cloud crushing simulation, like I showed from Matthew Abruzzo, and you include magnetic fields, it actually turns out that the cloud can sort of work its way through the magnetic fields rather than winding it all up. And so the process is very different. And so those simulations I showed of the cloud crushing, those actually include appreciable magnetic fields with a beta ranging from 100 to 10. And we find that it adds sort of order unity modifications without qualitatively changing things.
It doesn't change the fractal dimension of the turbulence, or the sort of Kelvin-Helmholtz layer.
So in this setup here, it would, because it would suppress mixing. It would, magnetic fields don't like to be bent, so you wouldn't be able to get that wiggly surface. But you don't have the same small scale dynamo in the actual, more realistic geometry like you have here. So you're safe. Yeah, and effectively the fractal dimension isn't really changed.
Okay, Amiel.
Drummond, that was a very beautiful talk. Thank you very much. I have two questions, two separate questions. First is, in your analytics and also in the numerical solution, when you treat the cooling, are you assuming an equilibrium cooling, or do you follow are you actually doing a non-equilibrium cooling on the fly? That's my first question, because that could lead to quite different cooling rates. That's my first question. The second question is, that beautiful picture you showed of M82, I believe that red stuff is H alpha. So you know more or less how much cold gas there is, and then there are also X-ray observations. The hot gas, the supernova rate is also known. So do the masses in cold and hot, given the supernova rate in M82, match your model?
Yeah, so two fantastic questions. Also, I had a fantastic discussion this morning with Alberto. There's not just X-ray in H alpha, there's also CO observation. So we can really get the full range of temperatures from 10 to 10 to the 8 Kelvin. So I guess I'll answer that first, then I'll go to your first question. So this set of solutions has a star formation rate and hot wind properties tuned to be quite similar to M82. And the reason why is because this simulation was tuned to be similar to M82. And so this is still early days. As an internal candidate, I wanted to be a little risky, show something new, So since you've heard a lot of my spiel before, so this is a plot I made 3 days ago. I haven't done the detailed modeling, but this is something we're really keen to do. And I think we have all the tools and all the ingredients to really try fiddling with some of the, and there aren't any really free parameters actually. So we can fiddle with the initial conditions and see if we can reproduce the properties of these M82-like winds. Now, to go to your first question about non-equilibrium cooling, this is something that's not included in this preliminary model. And actually, I just heard an incredible talk by Todd Tripp, which was really cool, where he showed some observations of oxygen-6. And for those of you who don't think about emission lines and absorption lines all the time, oxygen-6 is like everyone's favorite, but it got some really annoying quirks. And what he found is that he took some observations of oxygen-6 and re-observed them at incredibly high resolution and found that these big, broad absorption lines, consistent with the O6 being hot at around 300,000 Kelvin, actually broke up into smaller components consistent with the O6 being very, very cold at about 10,000 Kelvin. And this is exactly the case that Amil brought up, where you have non-equilibrium cooling. So the ionization state of the gas, of the oxygen in this case, hasn't kept up with the thermal state of the gas. So it's over ionized for its given conditions. And this is the beautiful thing of this model, is all of that is, I presented a lot today, so I didn't go into any more details, but that is something that I think would be a really natural thing to snap on. And Amil, if you're interested, I think, given your expertise on this, I would love to bring you in to help include that into this sort of modeling.
Thanks, great, we'll talk about that.
Cool.
Okay.
I think you should also give courses on slide preparation. You don't need a cartoon copy.
Well, I appreciate that.
Your skills are way beyond those of most of us already. Great. Okay, there's another question from Philip.
Hi, thanks, Drummond. That was a real tour de force. Enjoyed it. I was wondering, so when you showed some simulations of the cold cloud in the wind, and so I guess I have mostly a comment, and I'll pose it like a question.
Sure.
Yeah, that one there. There was a lot of work on a problem in liquid droplet breakup called bag and stamen breakup. And this is in secondary, what's called secondary atomization and combustion. And so since you mentioned combustion, I want to, and I think I was just wondering, since you seem to leave no stones unturned, I was wondering if you looked at that problem, because it is has a strikingly similar pattern, and in that case, surface tension is not really important because of the energies.
So have, I guess, left some stones unturned because I haven't heard of this, but I would be absolutely thrilled if you could send that to me and if we could even talk more about this, because I'm realizing that a lot of what I've been doing is actually sort of reinventing the wheel here, because a lot of this turbulent combustion, actually there's a paper from 1941 by a guy named Domkoller who discovered the Domkoller effect, which is this 1/2 and 1/4. Okay, so I'm can I do math? I'm 80 years too late. Okay, and so I think there's a lot to be learned from outside of our little sub world in astrophysical fluid dynamics. And it's one of the reasons why I'm so excited about A, being at the CCA, and B, coming to Cooper Union, because I think the interdisciplinary opportunities abound. And so Phil, you and I are going to have to talk afterwards, and you can send me a reference for that.
Thanks. I'll send you the reference. I think you'll like some of the pictures.
Great. I look forward to it.
They're black and white. I mean, there's no comparison to what you showed us, but.
Well, if you can make a beautiful plot in black and white, that's better than in full color, I think.
Are there any further questions for Drummond? We have enough time.
Stephanie has a question.
Stephanie has a question. Go, Stephanie.
I forgot how to raise my hand for a second in this version. Okay, so maybe it's in here and I just missed it. Apologies if so. But okay, so we've got this model for growth versus destruction, and a lot of it seems to kind of depend on our starting cloud size. So then in the simplest frame of this model, as long as I'm above, I don't know, whatever, half a kiloparsec, something like this, I'm going to keep growing. So where are these monstrous cold clouds? And I've been thinking about this a lot. I didn't see
Stephanie saying this. Sorry, I didn't mean to cut you off.
Yeah, I've been thinking about this a lot, and I haven't found that.
Good, perfect. And as I was trying to say jokingly, I promise I didn't see this question from Stephanie, because I actually haven't even shown her this yet. Okay, here's the answer without getting too technical. This C number, right, which is the crucial thing for if the clouds keep on growing, right? Well, I've called it, I talk about cloud size, but it's cloud size relative to, the turbulent velocity times the cooling time. So what happens as these winds expand out? The pressure drops, the density drops, and the cooling time increases very, very rapidly. So I have never been, if I start with a 10 to the 8 solar mass cloud, some huge honking cloud that has a C of, 10 to the 4 or something to begin with, by only about 20 kiloparsecs, the cooling time has become so long that even this huge cloud is going to start to grow. So I didn't include, I could, I'll show at group meeting tomorrow one of these plots, but this is a huge cloud down here, this sort of cyan color. It's 10 to the 6 solar masses, and it's gaining mass for the first 2 kiloparsecs or so. And then actually out here, it's actually losing mass. And that's because of exactly this process, that it's not just cloud size, it's cloud size relative to the turbulent velocity times the cooling time. And so it's the increase of cooling time as you move out that is so crucial. Think of a wind, it's adiabatically expanding, the density is dropping as roughly 1/r², and so your cooling time is getting really, really long. And the cooling time has
cooling floor. Do these have a temperature floor? Your runs? Because so let me before I do step-by-step questions, which are super annoying. You showed us your cooling time as a function of temperature, And,
Yes.
you know, where there's all this talk about like mixing layer, blah, blah.
Mhm.
But basically it seems like as long as any of my gas in my cloud hits that minimum of the cooling time, some of my gas should be whoppingly cooling and allow for cloud growth without
Yeah.
having thought like super carefully about this statement.
Yep.
So
Yep.
if I have my cooling floor set a little bit too high, then I might see cloud destruction, when in fact, if I allowed cooling to a little bit lower, like maybe I would just continue to see this rolling growth. That was my
Yeah.
thought.
No, good. So this is for a pressure of 10 to the 4 Kelvin per cc. So this
Okay.
is appropriate for the Milky Way's ISM has a pressure of 10 to the 3. M82's wind has actually a pressure of something very high, 10 to the 6, 10 to the 5, something like that. But the pressure drops is R to the minus 10/3. Okay, so that's a very, R to the minus 2 gamma. So that falls off very quickly. And if I were to plot this for a lower pressure, what happens is this minimum increases very, very rapidly.
I see.
I have a version of the plot I can show you actually. Do I want to do this on the fly?
No, don't do it. I'm talking to you later today.
Okay.
We'll talk about it then. This is very
Okay.
interesting, and I'm very intrigued to think about like CGM versus like ICM, where you're not having this like really dramatic change in pressures and stuff like that. But we can talk about that offline. Thank you for the answer. That was great.
I'll just say one final thing, which is that, I think Stephanie's question here embodies the importance of not just studying isolated individual idealized clouds, because in this case, the cloud grows forever. But when you put this into a realistic environment like an expanding wind, it doesn't grow forever. And so that is the interplay, right? That's the connection of scales. And that's what can only be captured with these next generation of, analytic models and cosmological simulation subgrid models.
Cool, thanks.
Yeah.
Okay, last call for any other questions for Drummond. If not, Drummond, I have a question for you.
Oh,
what kind of plant is that right behind you? It's really beautiful. With the heart-shaped leaves.
My babies, yeah. So this is one of my favorite plants. Wait, where's my camera? It's actually got some new leaves right now. Can you see these little guys?
Beautiful.
They're really gorgeous. It's a plant from South Africa. It's called a bombax. This is a dwarf version. They're actually a kind of tree. This is like a bonsai. But the bombax itself, they get these huge fat trunks with these little narrow, they look like this, but they hold huge amounts of water, and so they can survive in the desert for a really long time, or in between rainfall for a really long time. And this is one of my babies. It's actually doing really well here. So
that is super cool. I've never seen that before. All right, let's thank Drummond again.
Adrian did say he has a question. If we have the next minute.
Oh, sorry.
If we have just a minute, I'll ask a
We do. Please ask your sensible question.
Drummond, have you heard of the Smith cloud? Does that mean anything to you?
Of course.
Okay, good. So I don't have a great question other than that feels to be a piece of this story.
Oh my God.
It's been a long-standing point of confusion, for galactic gas.
Absolutely. So for those of you who don't know, the Smith cloud is, I showed the iconic galactic wind example. The Smith cloud is the iconic high velocity cloud, and high velocity clouds and intermediate velocity clouds are these cold, dense clouds. They honestly look a lot, maybe they look sort of like,
it looked like the movie you were just showing.
Yeah, exactly. And so these are these clouds that are above the Milky Way, sprinkled all around, and they're raining down onto the galaxy, or maybe they're actually moving out and being blasted by a wind. We can't quite tell, although it seems Milky Way has a pretty wimpy wind, so most people think they're coming in. Actually, I think for the Smith cloud, which we have the best data on, we do know it's coming in, and we've taken all these incredible observations from, you know, H1 up through ionized species. And, you know, I've been participating in this sadly virtual version of the KITP workshop the past month and going on for another month or so. On halo gas, and Mary Putnam has been there, and there's been a bunch of the experts on oh geez, I'm not sharing my screen. I'm showing all these things and I'm realizing I'm not showing my screen. Sorry. Whatever. I was just moving my cursor around in circles, so not missing anything. But yeah, I think this model is an incredibly attractive way to explain the existence of those clouds, and it's something that, you know, a lot of groups are really actively trying to pursue. So Adrian, that was a you know, a fantastic question and something that we really want to understand.
So what would you predict for the metallicity of those clouds? I mean, a lot of the HVCs are fairly low metallicity.
Yeah, exactly. So that's actually, God, I didn't include as many plots from my model as I would have wanted to, but let's think about this cold cloud, okay? So you start with a cold little nugget from the interstellar medium, which has solar metallicity. Then you throw it out into the CGM, and its wake forms, and that wake accretes, or, you know, there's a condensation flow onto the cold cloud, and that condensation flow is from the ambient low density CGM. So you actually expect the metallicity to be diluted as it grows more and more, because the CGM has a much lower metallicity than the ISM. So the metallicity constraints on the Smith cloud are actually they're very encouraging for this model. Yeah. And
Hey.
I'll just add one last really quick thing, which is Alberto and I, in our discussion today, he said that we theorists aren't making enough detailed observational comparisons. So we were talking about running a version of these cloud crushing simulations with really specific physical processes tuned to M82. And this discussion makes me think, well, maybe we ought to do a Smith cloud as well and do full post-processing, you know, hire a cadre of pre-doctoral fellows, get some Cooper Union undergraduates on this, and get everyone cranking on it. Because I think, you know, it could really be a revolutionary way to tie these, you know, detailed physical models to real observations.